Yeah. So thank you for organizer to giving me the opportunity. So today I'm going to talk about these like unconventional superconductivity in these bulk layered non-centrosymmetric transition metal dichalcogenoids. And bulk, why I am emphasizing, because we are getting the similar property by in these bulk systems. I will show you. It is basically comparable to like what you get in the few monolayer systems. So this work is ongoing work done by my three students like Tarusi, Chandan, and Palme is like final year student in collaboration with Professor Bahadur Singh from TFR and his student, and then Dr. Adrian Hillier from Rutherford Lab and Matthias Surer from Stuttgart. And the support is like we have various funding agency who supported this work. So what is unconventional superconductor? And so there are many type of unconventional superconductor, and we are particularly interested in superconductor where magnetism coexists. So you know this magnetism and superconductivity is both mostly it is largely incompatible, and they cannot, like in general they cannot you cannot realize them together. But there are few material where you can get superconductivity coexisting with magnetism, but they have different transition temperature. So like just before magnetism exists, just before superconductivity disappear. And before moving forward, I will give you more detail, but why you need this kind of superconductor. So one, like if I am talking about a superconductor where both spins are up, so it is called a spin triplet. If you are this kind of Cooper pair is there, when you apply, these can withstand very large magnetic field. So you can get better magnets and other things. You can get spin polarized supercurrents. Then you can also use for this spintronics devices, because you can get efficient spin injection. And you can also get the superconducting switch voltage control switching of the superconductivity. And now a lot of people are looking because it is needed for like all these non-abelian excitations like Majorana fermions and other. So lot of work is going in this area, but there is no concrete effort is there to realize this kind of triplet superconductivity. So this is basically this is a picture what for a student I am telling. This is like a conventional superconductor where you have the isotropic gap, but whatever we call unconventional, when the gap is gap is not isotropic, it have nodes or line nodes, point node. And first unconventional superconductor realized by, this is called FFLO state. It is like in 1964. Basically where you get this finite momentum pairing, and now you can realize by this can be realized in superconductor and ferromagnet heterostructure, but it is realization is difficult. So my group is trying to look various system where this kind of triplet superconductivity is a possibility of this kind of triplet pairing. So first we are the system we are working from beginning like last 10 years, it is non-centrosymmetric superconductor, because you have a non-uniform lattice potential. If you have center of inversion is not present, then you can get a non-linear lattice potential, and then it can break because parity is not good quantum number. Then you have the possibility of spin singlet and triplet. And our idea is that we can how we can tune this ratio. and basically you can tune by tuning the spin orbital coupling. The second system, like we are working here, mostly we work with the Sudeep. So this is a topological material, mostly here, like because SOC is very high, there is a, then your Fermi, like it break the Fermi surface, like Fermi surface, then here there is a possibility of intra-band and interband possibility, and then you can get a triplet superconductor in this one also. And also we are looking actively on the superconductivity in the low carrier system, because as low carrier, because you need a critical density of state, number density to form the to form the Cooper pair. But if it is not present, then there will be unconventional mechanisms are there to form that. So we are looking these low carriers material, and it is now very relevant for this Dirac and Weil metal, where like because of this linear cone, density of a state is very less. So we are trying to correlate basically how the superconductivity is happening in this system. And also we are using these high entropies alloys. Here we are mixing like 5-6 element, and we are trying to use these as a template to understand the disorder, control disorder on the superconducting ground state. And surprisingly, we found that even you have the different elements present with different molecular weight, we are getting the proper phonon mediated superconductivity. So it is still it is a puzzle how we are getting a phonon mediated superconductivity, and it is very robust superconductivity in these high entropy alloys. So so now, like recently we start working on these layer chalcogenides and natural heterostructure. So as morning talk given by Professor Anindam, he gave very nice introduction. So why we are interested? Because we can here tune the property, we can tune the structure, we can engineer the structure. So here you can see that like it have like lot of polymorph, and also we can we can create the heterostructure. So like a 4H, like this is a system. So if you look the 4H tantalum Sc2, it have 1H layer and 1T layer. One is superconductor, another is non-superconducting. But by doping the sulfur, simply by doping the sulfur, we make both the layer superconducting, and it basically give you, this is a kind of superconductor where you can get two different superconducting parameter in one bulk crystal. Then we are looking on these misfit compound, and why we are studying, because like misfit is, instead of a doping or anything, you put a spacer layer between these things. And if you look these like electronic structure or an RPES, you will only see the tantalum S2 monolayer property, and you will not see little bit electron transfer effect you are going to see from these layer. Otherwise you will get like proper monolayer property 1-to-1 what you do from the mechanical exfoliation. And also reason for the working on these metal chalcogenides is there, because they have very high charge like spin orbital coupling, but they are not many are superconductor, or they are superconducting at very low temperature. So by but they have, most of them have charge density wave, and by suppressing them we able to in many cases we able to induce the superconductivity or enhance the superconducting transition from the millikelvin to the like 2 or 3 Kelvin. So that was like one motivation to doing working on these chalcogenides. And why we are now interested in these non-centrosymmetric transition metal chalcogenides, because they have very high strong spin orbital coupling. So they can give you new phenomena like Eisen superconductivity, finite momentum pairing superconductivity, and of course it can give you the signature of time reversal symmetry breaking. So that was the motivation. And also we are trying to engineer these like layered material to realize the non-centrosymmetric like diode effect in these non-centrosymmetric system, because we can weaken the interlayer coupling and SOC is already very high. So we are expecting at very low temperature we can get these superconducting diode effects, which is generally people able to see in few layer devices. So we are trying to like realize these superconducting diode effects, and also we want to like these non-centrosymmetric material we can use because we can weaken the interlayer coupling, so we can use them as a devices instead of like going on the complex processes. So I will not talk about this one today, but I can discuss if somebody is interested.
Sorry, one quick question.
Yeah.
So this 1T or T variety does not break the inversion symmetry?
No, so we are working like there, like we are working on many systems. It is just general example. So this is the non-centrosymmetric.
Right.
This one is centrosymmetric. Okay, so I will come, like I will just here give, so they have like non-centrosymmetric and centrosymmetric both the structures,
Okay.
depending upon the material. Yeah.
Okay.
So these crystal is grown at IISER Bhopal. So we are using Brisbane vapor transport, optical floating zone and Chakrovsky method to grow these material, and then we have all the characterization facility to characterize it. So first I will talk, this is a 4HA NBSC2. So and this is also a non-centrosymmetric superconductor. This is a hexagonal, but like it is a different compared to the 2H structure, because we want to realize Eisen superconductivity in this one. So Eisen superconductivity is like if you have an inversion asymmetric material, then you can at valley points you can get spin polarization occur out of plane direction, and then this can give you the upper critical like field very high, and it will basically surpass the Pauli paramagnetic limit by 5-6 times. So, but the problem was Eisen pairing, like it was only observed in monolayers of 2H NBSC2. And when we try to look at what is the monolayer of NBSC2, they have the same like it is a non-centrosymmetric one, and they give you a very high spin orbital coupling, and that basically give you that very high SC2 and Eisen type of pairing. Then we realize this 4H NBSC2 have the same structure. The bulks 4H NBSC2 have the same structure. So it is similar to 2H, only one layer is little bit off, and it is giving you non-centrosymmetricity. And this crystal is grown at IISER Bhopal, and it is well characterized. It is very high quality crystal. And this is the density of state calculated by Professor Bahadur Singh group. And you can see that it is TC is a little bit less than 2H NBSC2. It is a 6.21 Kelvin, and the charge density wave is around 4.26 Kelvin. And it is a 2-gap superconductor, and this is the comparison. But when we measure the SC2 upper critical field, you can see that by all the, like we measure by resistivity, magnetization and heat capacity, we are getting around 30 Tesla. And that is the even in the bulk system, it is like it is a 3D bulk crystal, and there is still interlayer coupling. Still we are getting around 30 Tesla, and Pauli limiting field is like around 11.5 Tesla. So it was clearly indicating the Eisen type of superconductivity is present in this one. And to confirm that, we done the DFT, and all, like we found that this 4H NBSC2 material shows that like out of plane splitting up to 150 millielectron volt intralayer near to K and K dash valley point, and it is similar to that what is present in 1H NBSC2, and it confirms that it is like 4H bulk 4H NBSC2 is Eisen superconductor. And still we are working on the superconducting ground state, so it is showing a lot of other interesting property. We are getting the signature of some triplet also, so but I will not discuss that result here. So we are trying to make the 6H NBSC2 because we want to continue in that direction, but we end up with because sometime you have to add like third element to stabilize the structure. So we tried with that and we end up with the 6R NBSCT, and I realized already it is work by Sanjay. The mostly it's charge density wave and all the structural analysis. So it is like a bit different. Here it is like made of 1T and 1H layer, and but whole structure is non-centrosymmetric. So it is like a natural heterostructure, we can say that of 1T and 1H. So and it is very interesting to look that like how the superconducting property look like for these one. So this is the like we made high quality crystal. This is the lave, and you can see that lattice parameter from here you can see it is 3.57 and C is a very large, around 40 mstrom, and it is a superconductor around 2.1 Kelvin, and it is also shows a like BCS kind of behavior, and we try to fit it here like it is not well fitting with S wave, so it maybe it is S plus S. We are working on it, and you can see that like SC2 is around 5 Tesla, and it is breaking the Pauli limiting field, but it is not multifold, so we cannot say that it is like Eisen type of pairing, but definitely it is multi-gap. And it is also showing the 2D like this angle dependence of the upper critical field well fitted with these 2D models. So it look like interlayer couplings are weak, and it is showing the quasi 2D behavior. And surprisingly, when we done the further angular dependence of the SC2, we are getting the twofold rotation, like twofold variation of these SC2, and it is suggesting that maybe because it is 6R, so we should expect the sixfold, but we are getting only twofold. Maybe like sometime you can get in 6R threefold also, but here we are getting the twofold. So it look like twofold in modulation in magnetoresistance indicate basically rotational symmetry is breaking in the superconducting state. So it look like because and it is twofold, so it is not possible with only with the S wave. So it look like the superconducting ground state is like mixed. Maybe it is SP or something is a mix. So we are working in that area, and also it look like maybe it have a nematic superconductivity is present in this one. So further measurement we are doing it. So another compound like in the same line we try to look more non-centrosymmetric material. So we tried to work with this 3R tantalum SC2, and problem with the tantalum 3R tantalum SC2, it is very till now it is debatable because pure phase it is not stabilized. One Chinese group reported, but we don't trust because other people like till now nobody able to synthesize in pure phase. But when you put a like little bit tungsten, it stabilize in the nice 3R phase. So it is a non-centrosymmetric, and it is a like, and we this like we get very nice crystal of this one, and TC is around again here it is 2.8 Kelvin, and charge density wave is like presence is around 102 Kelvin. And here like we found that SC2 is like nearly double, and it is like look like here Eisen type 1 Eisen pairing is present. Heat capacity is also here, so the S wave behavior. Uh, Interesting thing is that like after doping we are getting a proper 2D superconductivity in this one. Like you can see that from angular dependence measurement, we are able to see proper 2D superconductivity in the like in this material, and it is verified by this BKT transition measurement also. And again here we are able to see the two-fold rotation. So now it look like this is a generic feature of these non-centrosymmetric chalcogenide material, because here it is again 3R, and why it is a two-fold modulation is coming, it is still not clear. But definitely like what I can think now, it is because of maybe it is not like pure S wave, but it have a subdominant contribution from P wave and RD wave. So we are like looking further on these compounds. So this is like ongoing work. So I can say that like our finding is suggesting that this non-centrosymmetric material with high SOC can be a novel platform to realize a lot of unconventional feature. And also by like doping this one, like we found that another compound also doping and intercalation sometime make these 3D like interlayer coupling very weak, and you can realize this 2D behavior. And we are also try to look now all this material by muon, STM and RPES to exactly see that what is happening, exact nature of the pairing symmetry. And also we are trying to see that because these are the bulk material, so we are trying to investigate the effect of interlayer coupling in the superconducting properties. And also we are trying to like trying to synthesize more super like material where we can realize Eisen superconductivity. And good thing about these bulk superconductors, Eisen superconductivity is there, like you can get now the exact pairing mechanism, because till now whatever reported on the monolayers only you can do the resistivity measurement. Now there are reports like it can, because non-centrosymmetric is there, there may be the finite momentum pairing is there or triplet is there. So now we can perform the experiment to verify that theoretical claims.